Okay, so yesterday I was talking to you a little bit about what one might expect astrophysically from as the source of the background that PTAs have observed, and so that's the subject of one of the problems that associated with my lectures. And so what I want to do first is to recap a little bit what I said before, and also highlight some of the things that you will be asked to do in this problem, so that when you do it, if you care to do so, you pick on those things. Okay, why those are interesting and why we were asking you to do those. So what I said was that last time was that a good way to get an estimate of what you might expect for the background of gravitational waves was to look at the supermassive black holes in galaxies, try to count them, and because the amplitude of the gravitational wave background, I was, I think, using the energy density in the gravitational wave background in some frequency range. There's some estimate that you can do by counting the number of black holes of a given mass, then the amount of energy being put out in a given, so this is the number density of black holes, black holes per commoving megaparsec per mass, and the amount of gravitational waves that on average that these binaries put out as they cross a given frequency range is proportional to the mass to the 5/3. I mean, there's some factors of the mass ratio of the binary and so on, but it's proportional to this. Similarly, the mass density, obviously, of black holes, that's just given by some integral, same kind of integral, just with the mass here, okay? And to get this estimate, a good way to do so was to just count galaxies, associate the black holes, the mass of the black holes in those galaxies by using the M sigma relation, and then assume that at some point in the history of the universe, those black holes merged at least once, and that gives you a good an estimate along these lines for the background, okay? So, so if you look at this, okay, you can use some canonical numbers for this black hole mass function. This phi of M black hole is called the black hole mass function. And it will look something like this. This is some sort of log-log plot. And the reason it will look like something like this is that this is basically a one-to-one mapping with the count of the number of galaxies as a function of their velocity dispersion or something like that. There's some sort of power law in the distribution of galaxies in one of these properties, but then by the time you get to very big galaxies, eventually, which have very high velocity dispersion, and as a result, very big black holes, there are not that many of them. In the universe, structure forms hierarchically, so smaller things form first, and there's the biggest things that have been able to form in the history of the universe until this point. So there's a big cutoff in the number of galaxies as a function of their sizes, and those are the ones that host the biggest black holes, and so the black hole mass function will look something like that. And if you're interested in one of those integrals like this, the integrand, how much gravitational wave energy you get from a given black hole, black holes of a given mass range, it will be given by this multiplied by, say, m to the 5/3 if you want to the gravitational wave background. So this curve, either of them will look like that. For the integrand for black hole mass or the gravitational wave background here. So this again, m of the black hole, and here's the integrand. So that tells you when integrand, whatever. It will look something like this. Here, the contribution will be very small from very, very heavy black holes because they are extremely rare. There hasn't been enough time in the universe to form big galaxies that could host those black holes if they follow this M sigma relation. And here, because even though there might be a lot of galaxies, smaller galaxies are more numerous, that increase in the density is not so rapid that would compete with this m to the 5/3. So the smaller binaries emit much less energy in a given frequency band, and so this will kill this part of the integral. Okay, so yeah. What's the power law of this phi? The power law of the mass function of galaxies is sigma to the so phi, the number density of sigma, maybe sigma to the -1 or something like this. So it's very, very kind of constant, and yeah, d log sigma is the same as d log m, so it's very, very flat.
So m to the -1.
Yeah, something like this.
So it's not the integral line look like this. Only the power one is like 5 times m is actually flat.
No, 5 times m goes, so I'm usually, maybe I want to plot d log m, and then it becomes, this is really, it's a log-log plot. So anyway, in the log-log plot, it looks like this, very much. So this integrated d log m, it looks like this. Okay. And this peak for the integrand of the gravitational wave background is something like 3 times 10 to the 9 solar masses. Okay. Blah, blah, blah. What else do I want to say? Okay, so so maybe, I mean, I'm saying like this, but we usually are doing like this, and maybe. So all of these things are in log-log plots. So that's more useful. Okay, so what else do I want to say about this? For the most part, in any astrophysical scenario like this, what you are trying to then, what maybe the first thing that you would try to learn from these observations is how many so we can count them some way, and then we want to see if from the gravitational wave of measurements we can get a consistency check or make some determination also about this black hole mass function, okay? To try to learn about the origin of these black holes, for example. And so the lower, if you want to describe this, basically there's some sort of normalization of this curve that you want to know about, like how many black holes there are. And then there might also be a location of this break. What is the place of this peak? Okay, those are the two lowest order things that you might want to use to describe what's going on here. You know, you could then try to add another parameter would be the width of this thing and so on. At the moment, with the data that we have, that's not something you can say very much about. So let's just stick for these lectures to trying to describe something about the normalization and where this peak is, okay? Or equivalently, you want to say, maybe I want to use as two parameters to describe this, the mass density in black holes, which maybe we can estimate some other way using the Zoltan argument, and the peak mass. Well, the peak mass, and instead of a normalization for this phi, some sort of, you know, phi star normalization, just rho of the black holes. How much mass density in black holes there are, and what is the peak? The peak contribution of these black holes, what is it? I mean, if you put canonical numbers, it's 10 to the 9, but perhaps the answer is slightly different. Okay, so so maybe your model will be that there is some peak mass that contributes, and there is the rho of the black hole. And as I was saying, the canonical numbers would give you something like this. Let me divide by some rho black holes star, which is whatever I get when I plug in the canonical numbers, the density of galaxies from Sloan and the M sigma relation, just the standard one that people like to use. So here is 1, okay? And here is like 3 times 10 to the 9. And this will be some sort of log-log plot. This is kind of the prediction, astrophysical prediction, if everything is the canonical. And the error of the size of the ellipse is from some sort of canonical guesstimate, just from whatever the observations are of the counting of galaxies and the M sigma relation. What dominates the size of those things is uncertainties in the M sigma relation. Now, if I try to, if I convert the black hole, the measurements from the PTA into this kind of quantity, I have some estimate from the gravitational background of something like this, okay, of this quantity with the correct prefactors and so on. So, so there's a measurement of that, and this, in terms of these two parameters, I could get the same background of gravitational waves by changing the peak mass. If I fix this, I can change the peak mass to change the answer, because they depend on different powers of the M black holes. So if I shift the up and down, both, if I shift phi up and down, both of them go up together. But if I shift the peak mass, the shape of this so that the peak contribution changes, those two things will change in different ways. So there is some line here where you get always, you get the same amplitude of gravitational waves. If you you can decrease, you get the same amplitude of gravitational wave as you follow this line, because, for example, you decrease the, as you follow this line, you decrease the rho black holes. But so let's say the normalization, you decrease this part, this integral goes down, but you are making the peak move like that. And because this one gets a higher power of the peak, you recover the same gravitational wave background. So there's, in this parameter space, the constraints from PTAs are some sort of line like that. So if you live anywhere here, you satisfy the measured value of the background. And what I was saying the other day is that if you put the naive numbers and you take this at face value and everything, here there is some sort of factor of 4 difference, okay? And you can account for this factor of 4. Maybe what's happening is that this is off, and you can try to say, oh, maybe the black hole, total mass density black hole is not bad, but I've screwed up the peak, so the black holes are a little bit heavier, and I get to here, or I have more density in black holes that I thought at this, and here it would be a factor of 4. If you want to make the black holes much lighter than this, then you need much more than a factor of 4 difference, because the black holes emit less, right? And so you need more of them. So another way of saying, if this is somehow if this is all taken at face value, I've counted these black holes in the galaxy, I'm missing some, what mass I could put them. If I make them much heavier than this, I don't need so many of them. I don't need to add much more density in black holes, because each of them are heavy and they produce a lot of energy. However, if I want to make them much lighter than this, I need many more. And so in total, because this power is lower than this power, I'll end up with a much more density in black holes. And then remember this, I can try to compare with the quasars or something like that, okay? So that's the game. That's what I was saying the other day. For the problem, so let me just flash the problem, what it is. Yeah, any questions about this? Yeah. Yeah, so you can say I've learned about the radiative efficiency. So I go and compare with direct estimates of the radiative efficiency, or I, exactly, yeah. This is all to learn about, in the case, if you go compared with quasars, there's actually two things that you can learn. One is this radiative efficiency, and also something called the Eddington ratio, which is the ratio of the luminosity of the quasars to this Eddington luminosity that I didn't introduce. But that is for a given luminosity of quasars, trying to assign a mass to it. So those are two things that people interested in accretion and so on care about. And those directly translate for a given luminosity of function of quasars into a rho black holes and an M peak. So if you want, you can translate this plot, if you care about that, into constraints of the radiative efficiency and the Eddington ratio. And again, these are constraints, for the average population. There's going to be a lot of scatter between them. What am I going to say? So I think, just what's interesting is that there's various ways to try to get, so we see these quasars, we see the black holes in the centers of galaxies and so on. There's now a new way of trying to get a sense or information about those masses and number density of those black holes, different from the canonical way that we have been doing it so far, which is by looking at quasars or counting galaxies, counting the black holes in galaxies directly, that can be put more or less in the same plane, and then we can try to understand all of the same things that we were trying to measure before, properties of accretions of quasars and the like. We now have a separate route to try to get at them. So I am not. So I'm not here to tell you, look, there's a factor of 4. It's time to include some gravitational waves from the early universe, primordial black holes, I don't know what. No, I'm not talking about that. I'm just saying that, good agreement, you could say, and also something is off. So let's try to understand what is off. That's the people that care about this will try to do it, but it's another avenue to put measurements on the same plot. So this would be one plane, the other one would be radiative efficiency and this Eddington ratio lambda for the more astrophysics of you. Any other questions? No? And so the final thing, now I will just advertise the exercise, which is the following. So this is a constraint, what you would learn from the amplitude of the PTA measurement. It would be something like this, okay? And you don't know where to put you don't know if the solution of, you don't know the peak, you just know this combination that keeps the gravitational background the same. But there's, so in addition to the amplitude, there's the shape of the spectrum in the PTA. So the PTA has measured the gravitational wave background in many frequencies, okay? And so the idea of the exercise is the following, or so to derive this, I did it the easiest way, which is I thought of a region of the universe as a box. I thought of the gravitational wave background's energy density in that, and so I just needed to count the number of sources, how much energy each source produced, and that's in the box, and that's all I needed to do. I didn't have to do very much. However, you can go around it in a different way. You can say each source, if I know the mass and the mass ratio and the distance, produces a given strain on the Earth, okay? So also something like this, you can get it by summing the contributions from all the sources, okay? Now, if you want to do that, what do you need to know? You would need to know or get in your model the number density of these sources, and then the strain that they produce on Earth, which depends on their distance. And so for that, you will, to try to integrate the effect of all the sources, you would need to understand like cosmological distances to a given redshift, the volume, and so on. And in addition to that, any given source spends only a fraction of their life in a given frequency band, right? So you'll have to take that into account. But once you know that, how much time the source spends in a given frequency band, and what's the volume to a given redshift, and if you have a model for the number density of say these black holes in the universe, you can write another integral which will give you the same answer, for the background. But also you can compute something else, which would be in a given frequency band the number of sources you expect that have a given, let's say, strain squared. Okay. So like some sort of luminosity function as a function of the strain of the sources. So how many sources that are very bright compared to less bright, and so on. This kind of number of sources per strain could be like similar to the number of sources per luminosity. In the optical, you can compute as some sort of integral along these lines, and that's part of the exercise. And the exercise, what it'll make you discover is that because of this effect, that the sources spend a different amount of time in different frequency bands and so on. The typical, for these astrophysically interesting models, the typical number of sources that you might expect in a given frequency band is very different. It scales very fast with the frequency. Okay, so even within something like a frequency to the 11/3, I think. Let me just make sure I don't screw up and tell you something. But it's part of your exercise. It's a very frequency to the -11/3, the typical number of sources. So as a function of frequency. So this means that, and not only that, it scales very fast with frequency, which means that even though the pulsar timing arrays have measured the spectrum only over, let's say, a decade in frequency, not so much, still there's a very large change in the expected number of sources that you should see in the different bins in frequency, or the expected number of these sources, okay? And furthermore, when you plug in the canonical numbers, this type of canonical numbers, what you expect from astrophysics, that number goes through 1, more or less, somewhere there in this band. Okay, it's not that it changes a lot, but it's a huge number all the time, or a minuscule number all the time. Okay, so it goes through 1, and the nature of what you expect to see in a situation where the typical number of sources in the given frequency bin is very large compared to the time when the typical number of sources of these, say, 10 to the 9, the ones that are supposed to contribute the most, are a small number, okay, is radically different, okay? And so the exercise will ask you to compute some sort of distribution for the strain squared that you might expect for different frequencies, and use that to say that if this peak mass, so remember, if we are trying to constrain this, when the peak mass gets large, we need to make the same background of gravitational waves, fewer number of black holes, because each binary emits more, okay? And so if you start increasing this, you get this problem that the typical number that you expect starts to become very small. And you will see that this dramatically maybe changes your expectation for the spectrum, because the source that in this calculation is kind of the average energy, but in any given realization, you might not expect to see in this frequency band any source, because they are getting very rare. And for typical astrophysical numbers, you don't need to do anything strange. You are in this regime in which you might cross the n expected number of sources equals to 1 in the middle of this PTA band, okay? And so that would change what you expect for the shape of the spectrum, and given that that is not seen in, and you will plot this and try, I mean, this is all qualitative, but you will do something in the exercise, you will be able to say that very high peak masses above, let's say here 10 to the 10, that's probably not a good solution to this problem, because they would lead to a spectrum that does not look like, or is not very well fitted by this power. Okay? Any questions about this? I'm just advertising the exercise, okay? But I think the one thing to take away that I think it's good that you work through it is this realization that for what we expect to see, somewhere in the frequencies in the range between periods of, say, 10 years and 1 year, or some depend on what you pick for this M peak, but especially once you get to 10 to the 10, this expected number of sources is both a very high power of the frequency, but also a very high power of the peak mass. The situation becomes quite different. And so there is an additional information from this in what has been seen. Okay? Any questions? Yeah.
So why is it relevant the strain square?
This you could do it for the strain as well. It's easier to do it this way. Qualitatively, what happens with this we can talk online. This one is easier, and qualitatively it gives you the same the same conclusions. You know, by the time, so if you want to do the strain, yeah, nothing easier for you. That's all. Any other question? Yeah.
So you said that in the middle of the band, at some point, there can be a transition where it goes from many sources to few sources.
Of this mass. So.
And when it is in the few source regime, then it is not Gaussian. Right?
Yeah, so the distribution, if you wanted the distribution from the strain square, it will look something like this. So when I said the typical number of sources, let me backtrack. When I said the typical number of sources, I said the typical number of sources of the mass that are supposed to contribute the most, right? So if those are gone, the ones that are a little bit less massive, which are more numerous, there's still a big number of them. And so you will get the background corresponding to a peak mass, which is smaller, because the heavy ones are not there, or rarely are there, right? So what happens is that in the typical realization, so if you computed the distribution of the strain square, it will look something like this. In the regime of very small number of sources, it will have a very long tail. Okay, the shape of this long tail is directly given by this dn dh square. So here I'm plotting some probability of h square as a function of h square. Okay, so what happens is that I'm losing in most of my realization, the most likely situation is that these very heavy ones, very heavy black holes, say, are not there. Okay, but I will get the background corresponding to a smaller mass. So I will get the typical realization will be one easy way to do it is to find the mass up to which you expect there to be one source, and think that that's most of the time what it is. And so this will give you the typical value of this peak, which is then the background that you expect if the maximum mass was that one and not the other one. But every so often, you will get, there's a chance that you will get one of those sources, which will make the average agree with that, because the average needs to be that. That's the average needs to be that the spectrum be this power law that you compute like that. So that the average is like this. So the average of this distribution, when you go to this regime of NC small, the average is here, but the peak is somewhere there, and then there's a very skewed distribution with a very big. But that's kind of the exercise. Yeah.
If it's like strongly non-Gaussian,
yes.
Then there will be some enhanced fluctuations about this hiding strength relation that Bruce developed.
Maybe I haven't thought about it, yes. Yeah, yeah. Well, the thing is that the Hellings and Downs, I think you get the same correlations for one source also. If there's only one source on the sky, you also get the same correlation. I don't know, you should ask Bruce. What? Yeah, you do it tomorrow. So I think it is the case that, and let me just say that when you look at this, what typically happens is that most of the time you have many sources that are not very bright. So the peak of this looks like a Gaussian, oops, okay, I will not be able to. So this looks, roughly speaking, like a Gaussian from a central limit theorem of the part of the mass, black hole mass function where the numbers are large, plus, you know, and then when you want to say the chances that I get a very high HC square is not by having two very bright sources, it's just one, okay? So plus the chances of one very bright one following this dndh square. In the middle, yes, a little bit the details of how the black, but for the most part, you're here and every so often you get a very bright thing. And so I suppose if in your realization you don't have any of these bright guys, you're still in the Gaussian kind of thing. I mean, of course, this breaks, depends on the signal to noise, how good, but roughly speaking, if you are, I think at the current time, I would say most probably you're either here or in the one source regime, which has not been seen in none of the beams because people look for the one source.
You get the same correlation with a single source, that is in the, if you move that source around, right?
I think, well, let me not say anything and Bruce can say the correct thing tomorrow. Okay, so that's the exercise advertisement. Any questions? Any other questions? Okay, so what I wanted to do next was talk a little bit about now backgrounds of more of a cosmological nature, just to advertise or try to get to, so there's a band of gravitational waves that is not the subject of this school, but are gravitational waves that we are searching by looking at in the polarization of the cosmic microwave background, okay? So I just want to get to some quickly trying to give you enough things to for you to try to understand what people are doing and why, okay? What are they trying to measure in the cosmic microwave background polarization and why that is sensitive to gravitational waves, okay? So let me just start by something that Bruce already said, which is that if you look at gravitational waves of a given frequency, that were created in the early universe at some point or another, their frequency gets redshifted as time goes, or their wavelength is increasing with the Hubble expansion. So lambda of the gravitational wave at time t, it was emitted with some, and then it will be A of t divided by A of t emitted. So, okay? And he made the comparison, which is a useful comparison I would also use, which is the comparison between the size of this gravitational wave and the size of the Hubble horizon of the universe at any given time, okay? So the Hubble radius, I will use just 1 over the Hubble constant, okay? And so I want to ask the question, or repeat, yeah?
Well, I want to make a comment, okay? This is really intended for you, but in relativity, horizon means the boundary of the past Cauchy development described to us. It has a very specific meaning. And I actually think we should say Hubble length. The word horizon is, in my opinion,
yeah, maybe I agree with you, but first I will just not be able to keep track.
People say horizon and they learn it because they hear other people say it.
Well, fine, but unfortunately, I'm not able to change the narrative of the world. Okay, so well, and there's also ways in which the Hubble horizon and the horizon around a black hole, people make analogies, for example, when we talk about the generation of fluctuations and Hawking radiation and so on, that are useful to make. So I think, anyway, it's not, you might not like it, but okay, whatever. And that's what everybody uses. You also don't like the Gaussian ensemble, but you did it also, right? So, so for the same, with the same excuse than the one I am using. What?
You're making me regret.
No, I think it's good. I mean, anyway, that's okay. So, so the Hubble radius, I'll try to do it for a couple of you know, there's many, for the purpose of these comments that I want to make, the Hubble radius for most, in most FRW cosmological matter era, radiation era, is just the time, the age of the universe. Hubble is 2/3t, 1/2 over t or something. So this Hubble radius is basically the age of the universe in radiation era, matter era. And so for the purpose of these kind of arguments, if the universe has a given age, and I wanted to make some, say I want to move matter so that is distributed with some fluctuations of a given wavelength, if the distance of that wavelength is too large compared to c times the age of the universe, I don't even have time to move things around or create those gravitational waves of this large frequency, put some source that is coherent with that frequency, if the age of the universe is not even long enough for that, right? And so in that sense, it is useful to make this ratio between the wavelength and the age of the universe or the Hubble horizon, okay? And so if you do this, okay, so this lambda is proportional to A, okay? And H dot, H goes upstairs now. So this is proportional to, so H is A dot over A, okay? And so the A's cancel, and this is proportional to just A dot, the time derivative of the expansion factor. So this ratio, whether or not this ratio is getting bigger or smaller, depends on whether A dot is increasing or decreasing with time, okay? So if you want, and that means that you care about the sign of the second derivative of A, whether A is accelerating or not accelerating. So during most of the expansion of the universe, with the exception of this time now, the expansion of the universe has been decelerating, okay? And so A dot is decreasing with, A dot is decreasing with time, okay? So, if there is a period of accelerated expansion, the situation changes, okay? So the relative size of the wavelength to the Hubble horizon changes how it evolves. So sometimes it is useful. So I will just do a similar plot that the one Bruce did, but I will, instead of plotting the wavelength and the Hubble radius, I will just plot the comoving wavelength. So with the factor of A taken in, so that in those coordinates, the wavelength is just fixed, okay? So, so the comoving wavelength of the gravitational wave is just a constant now. Basically, I'm plotting lambda divided by A, lambda of t divided by A. So the size of it today, if I do put the A on the other side. Okay, so so the wavelength is constant in this. So these are comoving coordinates. Comoving. And this is time, or A. And so during the normal periods of the expansion of the universe, then the universe is decelerating, which means that the Hubble horizon is, or the Hubble length is going faster than this lambda. And so it will look something like this, okay? So this would be the Hubble radius. Moving again, okay? So we are somewhere here in the late universe looking at a gravitational wave, okay? And so we go back, we go back, we go back. Eventually, the size of that gravitational wave becomes comparable to the horizon. And so it will be not feasible to create that gravitational wave at any time later than that, because it would involve having regions that are separated more than the age of the universe somehow act together to create these gravitational waves. I mean, okay, so when I was talking about the astrophysical background, we are here. The black holes that produce the PTA things are also here, no problem. Everybody is well under the horizon, okay? But if I go back, eventually any given wavelength, I can create them astrophysically or maybe people would call, if the creation is close to the time when the wavelength is of the order of the Hubble radius, you would call some sort of cosmological thing, some phase transition and stuff like that, or some cosmic string network or something of this nature, maybe are creating gravitational waves comparable to the horizon at any given time, and otherwise much smaller, but I cannot go on this side, okay? Any questions about this? Comments? Okay. But then I could ask the question, so, I mean, something like this. I could ask the question, let's say the Big Bang or the hot Big Bang thing starts here somewhere, okay? So this history of the universe, that is the radiation era, matter era, and so on, starts at some point from there forward, okay? Could there be gravitational waves already at the very beginning there of size which are much larger than the Hubble horizon at the beginning of this hot Big Bang model of the universe, okay? Could I have something from the beginning, from the Big Bang? It's already there. I started with the seeds for these gravitational waves already in place. They are there, and eventually when you're here, they are oscillating around and you can measure them, but they were there from the very beginning, okay? Possibly, we don't know what the very beginning is, so we could ask the question. And okay, and it's not such a ridiculous question, because we already know that there are things, we have found things that come from here in some sense, which is the following. The same thing that we are saying about gravitational waves, we can ask the question, the fluctuations that we see that lead to the development of large-scale structure, the formation of galaxies, the temperature anisotropies in the CMB, when were they created? Their size also changes with the expansion of the universe, just like this. So this lambda of the gravitational wave could be the wavelength of a perturbation that then leads to galaxies or the hotspots that we observe in the CMB. So same blah, blah applies. If I'm going to make them in the universe, so I go back, I can make them anywhere here by some sort of process, a network of cosmic strings, moving things around and creating differences in the density from here to there that then can grow to form galaxies or whatever. But eventually there comes a point in which, the same story, they become larger than the horizon, so those things are not operative, and at least with this, anyway, those are not operative. And when were these things created? Now we know for a fact, like theorem, that the fluctuations that grow to make the large-scale structure were already here, okay? Wherever you start the hot Big Bang, they were already there. So if those were already there, why not some background of gravitational waves? Perhaps, why not? Usually what we do is just not to say, oh, there's abracadabra, Big Bang, and everything was there already. We do slightly one additional step, which is we try to extend this history somehow and come up with some process of something happening before the start of the radiation era, that would make this not look abracadabra, but that we can do something, write some equation or something like that. And if I wanted to do this, I need this length scale to now have a different slope, so that something that is much larger than the horizon length or the Hubble radius length at the beginning of this hot Big Bang era becomes much smaller than the horizon in the past somewhere, so that some process that I'm cooking up can create it. Okay, so I need some history of the universe where this Hubble radius in this coordinate first decreases. And so I now have some period of time in which I could create these density fluctuations or the gravitational wave background. Then, so I need this comoving volume to go down, which, as that formula indicates, I need a period of accelerated expansion. If there is one option is to have an A dot positive and also accelerating so that the ratio goes like this, okay? So this is inflation, but maybe something else happened. But so if the universe went through such a period, then maybe I have an option that not just the density fluctuations were created here, but perhaps some gravitational waves were created here as well, okay? So that's the idea. And what I was telling you is that we now know that there are, the fluctuations at least come from this, I mean, were there for the purpose of the hot Big Bang, they were already here. If you want, you can add some story here and create them in your favorite thing, inflation or something else. But by the time the radiation era was around, they were already outside the horizon there, okay? How do we know that for a fact for the density fluctuations? We know it in the following, the simple way that we know it is the following. Imagine, so when we look at the cosmic microwave background, that radiation comes from a given time in the history of the universe when the hydrogen atoms combine, when the electrons and protons combine to form the hydrogen atom, which we call recombination, okay? So it comes from this time, okay? So we can ask the question, let's look at a wavelength on the sky that when I extrapolate it back, the place where it crosses this Hubble horizon is that time of recombination. Okay, let's look at that on the sky. That substance we can compute, and that's roughly like a degree scale fluctuation on the sky. And so I can ask the question, so if the fluctuations were created well inside the horizon, then there shouldn't be any fluctuations there, okay? And so I look at the biggest thing that could have been formed if all that there was this, okay? And I see that there are fluctuations. So first thing, there looks like there are fluctuations on those scales. So I have two options. Either something is happening very fast at horizon crossing, right at this point, something is happening, matter is getting rearranged so that I see that there are fluctuations on those scales, or they come from the past, okay? So how do I know that they were not just happened to be formed at that time, the fluctuations that I see? So I can go to the microwave background and look for different regions. There are some regions that are overdense at that time. So I look at the cosmic microwave background, look back. I'm looking at various regions in the universe at this time, okay? And so some of them, the density is higher. Some of them, it's a little bit lower by 10 parts per million, something like that. Fluctuations of 10 to the minus 5 from. And so I can take a look at the places where the density is a little bit higher. I can take a look at the places where the density is a little bit lower than the average. And I can ask the following question. So this we can do. We have the map by now of the CMB. We know how the temperature of the CMB relates to densities at the time. So we can pick the overdense, the underdense, we can do that. And then we can ask the question, so there are fluctuations on this scale that is the maximum of the time. Are they being created when we are seeing them or not? How would I know that? If I am creating this overdensity, for example, then the velocities need to be pointing towards there. I had a universe with no fluctuations, and there's some mechanism acting at the time that's creating these overdensities just in time, as fast as they possibly can, okay? So in that case, the velocities need to point towards this place. If, however, I started with an overdensity, and suddenly the Hubble radius is comparable to this overdensity, and the material realized, oh, this place has more density, and also as a result for this fluid, more pressure, this will launch some sort of wave that will try to smooth this out. And so the velocities would be moving like that if this was there from before, okay? So I go look at these maximum things, and I ask the question, are the velocities going in or going out? Okay, and this tells me, was this thing there from before, or is it being formed at that time? And we can measure velocities at the last scattering surface by looking at the polarization of the CMB. And so the divergence of the velocity is directly related to the linear polarization of the CMB. I'll tell you a little bit about that in a second. But so there's a question about the sign of the divergence of the velocity versus the sign of overdensity, underdensity. That's the test. And we go out there and we see this situation. We don't see this situation, okay? Observation, okay? So by measuring the velocities of the plasma using the polarization of the CMB, we know that at least the density fluctuations were there before this time. So they came from now, there's no process being able to make them or change them when they were very large compared to the horizon. So for the purpose of the hot Big Bang, they come from here, okay? Now we might add something in some inflation period or something else and try to create them. We need to do something like this, or maybe it's abracadabra string theory, I don't know, but they come from here, okay? So the question of whether there is a background of gravitational waves that was also there at the time, I think is a fair question, okay? Any question about this, any comments? No? Okay, so now the final thing that I wanted to mention is, okay, let's say there is a background of gravitational waves. How is the CMB sensitive to it? Why, by looking at the cosmic microwave background, I can know if there is, if there are gravitational waves in the universe everywhere. In particular, they were also there at recombination, and they were affecting the electrons and the material over there and doing something, moving them around. If they were there moving things around, how can I tell? Okay, is there a way to tell? And luckily, there is a way to tell, and the answer goes like this. So it goes to the polarization of the cosmic microwave background. So let me just be very quick about this. So we are here, we look at the radiation from far away, the microwave background or whatever it was. In the case of the microwave background, the universe has been transparent for a very long time to the photons of the cosmic microwave background for the most part. And so they are coming from very, very far away. When you go sufficiently back in time, there is this period of recombination in which before that time, you had protons and electrons separate. After that time, they formed hydrogen atoms, okay? Now, the cross-section for light to interact with the charged electron is much larger than the cross-section for light to interact with the hydrogen atom. So the moment back in time, so this is, I'm following the trajectory of some light from the cosmic microwave background back in time. The moment I get to recombination, and now instead of having hydrogen atoms here, you know, little hydrogen atoms, blah, 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 I now have electrons and protons separate. Now the cosmic microwave background scatters with the electrons very efficiently. So if I follow the path of the photon, it does like this, and then it starts random walking like that, okay? Because it's scattering with the electron. The density is also increasing with time as the universe, or decreasing as the universe expands. So as I go back in time, the density of matter is going up, so the mean free path of the photon is going down, 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 and so these steps of the random walk get shorter and shorter and shorter, okay? So when we look at the cosmic microwave background, the photons are coming from here, from one specific region, okay? And in some sense, we cannot see anything.
Question about the mental picture. The photon's not actually scattering. It's not keeping its identity. It's actually being absorbed and emitted.
Not anymore. So it depends when you go back. But, you know, there's a time when the...
a little bit of fraction, 1,300 to 1,500.
No, for a long, very long time. So you conserve the number of photons. That's why if you do anything, you inject energy into the cosmic microwave background. Yeah, so you change the spectrum. So if you look at, it's true that as you go back, eventually there are processes that emit photons, and eventually the cosmic microwave background thermalizes with everything else, right? So if you go back in time, the scatterings, creation of photons, annihilation, absorptions, they are so very fast. That's why the cosmic microwave background is a black body spectrum. You were in thermal equilibrium. But much before redshift of 1,000, those processes become too slow, and you end up with a cosmic microwave background with no creation or annihilation of photons anymore. You conserve the number. So there's a period of time where you cannot thermalize the CMB anymore. And so, for example, people study, that's why people are interested also in looking at the spectrum of the CMB, because if I see a spectrum that is not a black body, it might tell me about some processes that were injecting photons or something like that in some period. If it happened too early, it gets thermalized, but there's a period of time in which I'm not. So anyway, that's a side note, but for the purpose of the cosmic microwave background, yeah, follow the photon, and then it has a very short mean free path, okay? Now, when photons scatter with an electron, they can get partially polarized. If the radiation incident on the electron is not isotropic, the resulting light is a little bit polarized, a little bit linearly polarized. If the radiation incident on the electron has a quadrupole moment, in fact, if you're a little bit, so if the pattern of radiation has a quadrupole anisotropy, more light, I mean, coming, say, from the top and the bottom than from the sides, then the part that scatters towards you will be a little bit linearly polarized, okay? So if there is anisotropic radiation incident on these electrons, there will be a little bit of linear polarization in the cosmic microwave background. And so the effect of both gravitational waves and density fluctuations is to create anisotropies, just as the same as the anisotropies that we see, the same morally, of the anisotropies that we see in the sky today were seen at some level by the electrons. It's just that we see they're coming from very far away from us, the photons. But for the last scatter, let's say there was a scatter here that led to the photon that we observe. This electron was seeing radiation from a small region around it of the size of the mean free path. And just as we see a little bit, or we see, all the multiples, the CMB is anisotropic, this electron also sees an anisotropic radiation if the universe was not perfectly homogeneous. So if there's density fluctuations, for example, let's say this electron is moving at certain velocity, but the material over here is moving at some other velocity. There will be a little relative Doppler shift between here and here, and this will lead to a little change a shift in the frequency that is equivalent to a change in the temperature, and so there will be a different anisotropy due to that in the rest frame of the electron. Also, if there is gravitational potential fluctuations, there will be a gravitational redshift between here and here if there is a background of gravitational waves, the gravitational waves will, just the same formula that Bruce wrote, the integral of H dot, they will create along this little path some redshift, and so it will create some quadrupole as seen by this electron. And so that anisotropic radiation will create some little bit of linear polarization, and the light that we observe here will be a little bit linearly polarized. Now, of course, the same gravitational waves will also make these changes between here and here, so they will make anisotropies in the temperature as well that we would observe. Why focus on the polarization, okay? So, so why focus on the polarization? So gravitational waves and these density fluctuations create anisotropies of the temperature that we observe and create little polarization, a little bit of polarization fraction for the radiation that comes to us. So we can think that when we make a map of the cosmic microwave background, we report in each direction on the sky, we report a temperature and a linear polarization. So we need to say how polarized the light is and in what direction, okay? And for each point on the sky, we have a map of temperatures and polarizations. That's what we measure. So the reason for focusing both, if we are discussing polarization, both density, homogeneities through these velocity effects and the cosmic microwave background and background of gravitational waves would create anisotropies here that through a scattering will lead to linear polarization. So the linear polarization is produced not by the gravitational waves, but it's produced by the Thomson scattering, by the scattering with the electrons of the anisotropic radiation that is created by the velocities or by the gravitational waves, okay? Both of them lead to a little bit of polarization, okay? Good. So what's special about the polarization in terms of the being able to see gravitational waves? So let's just do the following. So imagine that you're here, and this, let me put here the z-axis, x, y, okay? And there is the last scattering surface, okay? Very big, this place where the photons come from, some sphere around us, okay? And let's imagine that there is a single gravitational wave or a single density fluctuations of a given wavelength, Fourier mode, a single Fourier mode, okay? So let's say if it's a density fluctuation, I will decompose, just as you're doing for gravitational waves, the background of gravitational waves or the background of density fluctuation as a superposition of Fourier modes. All of these fluctuations are very small, so I can think of one of them at a time. So the problem that I need to solve is the one with one Fourier component of either the gravitational wave or the density fluctuation, and see what happens, okay? So for example, I could imagine a universe where there is, along the z-axis, some plane wave of density fluctuations. So here, the density of the universe in this plane is larger. Along the z-axis, here is smaller, here is larger, some sinusoidal pattern, okay? That's a big wavelength of size similar to our sub-Hubble horizon, or a factor of 10 or 100 smaller than that, okay? Or it could be a gravitational wave, okay, of this similar, okay? Now, when I look here, in this direction, the photon comes from here, and it's coming actually from here. When I look, it's coming from here. So when I look at the cosmic microwave background in different directions on the sky, I'm sampling what the effect of this long wavelength gravitational wave or density fluctuation was over here, over here, over here, over here. Is this clear or not? Okay. So what I will try to understand is what is the pattern of the direction of the polarization that will be produced by this Thomson scattering. Produced if here there is a gravitational wave, or here there is a density fluctuation. So as I change the direction on the sky, in what direction is the light polarized? So probably it will be polarized in one way here. Then by the time I get to the place where there's an underdensity, maybe the direction of the polarization is slightly different, and it will change on the sky depending on what was happening in this spot. What kind of quadrupole anisotropy was being created on the electrons here that then through the Thomson scattering led to the polarization that I'm going to observe here, okay? So there will be a pattern on the sky produced of polarization and also of temperature anisotropies produced by this one single Fourier mode, okay? But it'll turn out that because of symmetry, this pattern will be very different if the thing is a gravitational wave or a density fluctuation. How come? So linear polarization, as I was telling you, you need to specify how polarized the light is and in some direction. So you put a polarizer, you rotated it, and you can do various things. You can find the orientation where you get most of the light through. That's one option. Or you can take the polarizer in one direction and see how much intensity you get and do it in the 90 degrees and see how much light gets through and subtract these two things. Let me call this I1 and this I2 and define Q, which will be I2 minus I1, for example. And then I could repeat the experiment with the polarizer like this, 45-degree rotated. First like this and first like that and then like that. Call this I1 and I2 and measure again the difference in the intensity. It turns out that any linear polarization, if you measure these two quantities, or you measure this difference and then rotate the polarizers by 45 degrees and measure it again, you call this U. These are called Stokes parameters. So E2 prime minus E1 prime. This would be the 2 prime, 1 prime direction. And you can pick it doesn't matter which directions you pick as long as you do it one way and then rotate 45 degrees and you do it again. If you measure these two differences, any linear polarization can be described with those two numbers, or equivalently, how much polarization you have and in what angle it's maximum or something like this. When you rotate the polarizer, when you get the maximum, what polarization fraction you get, and what was the angle. Those are two equivalent ways. This way, by the way, just to make a connection, of course, the numbers that you will get if you do this experiment will depend on how you oriented these two to start with. If you did these ones for Q and this one for U, you'll get one thing. But let's say I started with some different orientation by an angle psi for define Q with something else, and then rotate 45 degrees and do another U, which will be with different coordinates, okay? The answers you will get are different, but the way they transform with these rotations. So instead, I have the Q with these polarizers like that, but now I do it again with some other angle psi, right? An angle related to this equal to psi. The combination Q plus IU transforms the new ones, has spin 2 or something. So the same, the numbers that you get with the new coordinate system are related with the old in this way, okay? So the math becomes the same as Bruce might or might not do for H plus IH cross, okay? So the spin 2 spherical harmonics are the thing that we use to characterize the CMB polarization as well, okay? And it's very related. The point of the gravitational waves creating a pattern on the sky that is different than the density fluctuations is very related to this fact, in fact. Okay, so we have these quantities Q plus IU. So let me just do pictorially what's going to happen, okay? So let me ask the following question. Let's say I have some density fluctuations in the early universe. So in this plane wave. So here is positive density, negative density. I start with something like that at the Big Bang. Positive, negative, and I let it go, okay? And let me look from the North Pole. So let me look from here and try to plot the direction of the polarization that this person will see when it looks around the circle, okay? So let me just focus on like a little region here around the North Pole, just to make it easier, and ask you to tell me what can be the direction, what can be the pattern of the polarization that an observer would see if there was this gravitational, this density fluctuation in the universe, and it moved and so on. Of course, you cannot tell me because you need to equations how things move, the polarization. But there were certain things that you will be able to tell me. So let me draw then. I'm looking from the top. This is the z-axis. Then let's say this is the xy plane. Okay. So here's x and y. Okay. And I want you to tell me something about the pattern of the polarization directions. If the cosmic microwave background will be polarized in some direction, what this pattern could be. There's only this density fluctuation, okay? What it could be. I don't know. You probably, the first answer would be you don't know, true. But there are certain things you know about the pattern. The problem is a linear problem, right? There's only this guy, okay? So it has certain symmetries. What symmetries it has? It has some symmetry of rotation around this axis, right? So if you plotted here, so here is the z-axis, right? So if you said, oh, the polarization here was this one, then you can draw whatever is the pattern. You can draw a circle like that, and it needs to be the rotated version of this all around, because this problem has this symmetry, okay? So I don't know. Maybe you will not be able to tell me if here it's oriented in what way or in which other way, but if you tell me one, for any given value here, you will know to go all around, okay? And then, so is this clear or not? Yeah? So now, so for each radius, you will need to tell me in what direction it is polarized. Could be it's not polarized for this direction, it could be it's in this direction, it could be in this direction, then you rotate it around, okay? Second thing you can tell me is, okay, am I allowed to plot? Let's make some pattern. Let me give you two examples. Okay, pattern like this, so all radial around, or let me give you three patterns around this point, and you tell me if it's a possible solution. Okay, one of them is the center here, and they're all radial around this point. Another option, it would be all tangential around this point, okay? And let me do a third pattern, which would be, for example, I take all of these, I take this one and I rotate it by 45 degrees.
Here's a question. In your tangential pattern, is there an arrow and a tail? Is there a direction or just a parallel line?
No, it's just a parallel line because it's linear polarization. And if you rotate the polarizer by 180 degrees, you get the same, right? It's not vectors. So, okay, so, but this tells me, okay, let's hold that thought. So these are just directions of in which the light is most polarized. So if you put the polarizer where you get the most light going through, okay? And in each place you rotate and you find that direction, you plot an arrow in this direction. You plot a line in this direction, not an arrow because there's no meaning in the polarizer like one way or the other, okay? Good, so they are not arrows. So this is not a vector field, but close. It's really a spin 2 field. If this quantity is transformed like e to the upside, then I would start putting arrows with no 2, with the 1, okay? Any other question? Okay. So these were two patterns, and I was doing some third pattern would be, let me rotate everything there by 45 degrees in one of the locations. So I will be very bad at plotting this, so I will first do that. Okay, so let's say I look at some particular radius, and I tell you the pattern of polarization is that one, or that one. Are all of these patterns allowed for this problem? You don't know how to solve the equations, but based on the symmetries only, are they all the same? fourth pattern, which would be if I rotate 45 in the other direction, right? So it would be like that, okay? Anybody wants to guess something? Say something? Yeah?
So I would guess, this is very nice, I haven't thought about this, but I would guess the top two patterns are both allowed because your plane wave density perturbations traveling up has complete rotational symmetry, also reflection, and the first two there are reflection and rotation symmetric, but the last one is not reflection symmetric. So I would guess the top two are allowed in combination.
Exactly. So the question is about reflection symmetry, because I drew them such, I tried at least to make them that when you go around, I plotted one and then I do the same thing going around, right? So the part about the rotational symmetry, fine, I already took care. Everybody satisfies this. The four patterns, if I had managed to do the fourth one, would also satisfy this. However, the first two patterns, if you put a mirror in any direction there and you reflect around that mirror, it will give you the same pattern. It will go through, nothing will change, okay? However, this one, if I put a mirror here and I rotate, then I get the fourth pattern that I didn't draw, the one that had the thing 45 degrees in the opposite direction. So those two patterns are even with respect to some parity. These ones are odd, okay? Another way of saying it, if this was instead of field of spin 2 things, this Q plus IU, it was a vector field, those two patterns there are things that you would get by being the gradient of some potential, while these ones on the bottom would be what you get if you're the curl of something, okay? So that's kind of gradient type things. These are curl type things, okay? So you could call these patterns gradient patterns and these curl patterns, okay? Now, what happens if I have a gravitational wave, okay? Again, the polarization origin is the same for density fluctuations of gravitational waves, is Thomson scattering of some anisotropic radiation, okay? And for that, we solve all the radiative transfer equations, we solve the equation for the gravitational wave, we do it, right? But I'm just trying to jump to the answer, okay? So in the case of gravitational waves, now you have these two polarizations, okay? Or you could form these helicity combinations that Bruce was talking about, right? So exercise or think about it. If you just have one of these helicity components, no longer do you have this parity symmetry, or if you talk about the plus and the cross polarization, the parity symmetry of the problem will be restored because the universe, let's say, is parity symmetric on average, okay? However, the size of gravitational waves in a given realization of one particular Fourier mode of frequency of gravitational radiation of the cross polarization or the plus polarization might be different. If on average, then the power in those two sides would be the same, but one or the other will be different, and then the pattern that you would produce if you have, say, one of these helicities and more than the other, it will be different on the sky. It will not respect this parity symmetry, okay? And also, if you think of the plus and the cross, there's, yeah, so anyway, so you can, with gravitational waves, you can create this kind of pattern, okay? But you cannot create those kind of patterns over there, okay? Okay, so I'm super out of time.
The opposite you finished with the density perturbation. Density perturbations can be the top two, but not the bottom.
The density fluctuation, the thing is, the density fluctuations cannot produce this because they respect parity. The gravitational waves, a given one single then can create this and that, both of them. So if you decompose, so at the end of the day, you can solve the problem of the radiative transfer of this gravitational wave pattern of polarization. You will get a map on the sky for a given wavelength of polarization of this Q and U that is produced everywhere. And you can ask the question, does this pattern, I can decompose it into some basis of or the part that is the gradient part and the curl part, just like a vector field. There are two potentials called E and B, which you can decompose to an arbitrary pattern, one of which is odd under parity, the B or the curl part, and one which is even under parity, the E part or gradient part. So any pattern produced by both gravitational waves and density fluctuations can be decomposed in that way, and also the one on the sky. If there's only density fluctuations on the sky, they cannot produce by symmetry the curl patterns. So you should take the, if you thought, instead of being polarization was a vector field, you have the vectors of the polarization on the sky, you compute the curl. Density fluctuations cannot produce a curl, so you should see zero. But if you go make the experiment and see all these arrows, take the curl, and it's non-zero, there's some noise in the experiment, so well above the noise, then it means there's something that can produce a curl, cannot be density fluctuations. Gravitational waves can do it, and that's how we can see if the, something was there left over from whatever produced the density fluctuations, whether or not it produced also gravitational waves. So that's the goal of the CMB polarization experiments that are trying to map out the polarization of the CMB, then decompose it into the gradient and the curl, and see if you see any non-zero curl piece of this spin-2 thing, spin-2 field of Q plus IU. And if you do, you know that there's something else in addition to density fluctuation. Now, it's raining so badly that I don't think we can get out of here. But anyway, any questions? Yeah. Sorry? Oh, what hasn't been done? So first of all, the degree of polarization of the CMB is not 100%. Okay, so it's more like 10%. It depends on the angular scale, but it's more like 10%. So the measurement of polarization is more difficult than the measurement of the temperature. By now, the measurement of the polarization has already been done as well. There's an additional question, which is how big the gravitational wave background is, if at all. Okay, the smaller it is, the smaller the polarization it produces, the smaller the, remember the polarization is produced by the anisotropies created by the gravitational wave background. If the strain of the gravitational wave background is smaller, they produce smaller anisotropies. The size of the anisotropies is nothing other than this H dot multiplied by the mean free path. So some simple-minded, these wavelengths are very long compared to the mean free path, and so the integral equation that for the frequency shift that Bruce wrote down is just the value of H dot multiplied by the little distance. Something along these lines is the size. So you start decreasing H, the level of polarization is smaller. So in fact, people have measured polarization, have looked at the amplitude of the curl, have not seen any curl, and on the basis of that, have put some upper limit on the strain, okay? And then we will have to get into, did you expect a strain bigger than that, smaller than that? And then it will depend a little bit on the abracadabra that you're putting before, and I'm happy to go offline on that, because there are some expectations, and some of which are perhaps the most reasonable of which have already been ruled out through this method. I don't know, the most reasonable is a very loaded because it's abracadabra stuff, so I don't know. But anyway, the canonical inflation model that people would have taught, and probably I would continue to teach because it's the simple thing to do a calculation. So m squared, phi squared potential, something that produces more gravitational waves than what have been the upper limit. Okay. Any other questions? Yeah. It respects parity, but it respects parity now on average. So in other words, everybody here, the average is going to be 0, but also respecting parity for the gravitational wave background would be that the typical the variance of this pattern and the variance of the opposite pattern have the same power, right? It's not that you create a universe with a preferred handedness. So as much of this you would see as of the other pattern in the distribution. If you think of this, the value of this curl component, it will be distributed in the simplest way as a Gaussian. The variance of this Gaussian for the curl part with the one parity and the curl part with the other parity will be the same. In this way, the gravitational wave background of the universe most probably respects parity. It's about the abracadabra. You can create some abracadabra that breaks parity, and then you have a preferred direction.
Can I give a different answer to that question?
Mm-hmm.
Here's another way you can do it. Remember I was talking about constructing ensembles? So construct an ensemble of universes this way. In universe number one, when you look at the sky, in any direction, you see a circularly orbiting binary pair. But it's always orbiting counterclockwise. So I look over there, and I see it, there's a circularly orbiting binary pair. I see the circle and the plane that I'm looking at, and it's counterclockwise. I look up there, it's counterclockwise. That's the first element of my ensemble. Next element of my ensemble. I look up there, and it's rotating clockwise. That one over there, rotating clockwise. That one over there, rotating clockwise. The ensemble effort is unpolarized. Any quantity that I calculate, it's equally likely that one realization has it going one way, the other realization has it going the other way. But any given instance, any given representative universe, it's completely circularly polarized. It might be right-handed or it might be left-handed. And so the variance, the deviation away from the average value across all universes is unpolarized. You have no access to that though, right? And so you see the variance when you is basically one. It's like my example where the mean value of z was 0, but the mean value of z squared is 1. So that's another way of constructing an example with your properties.
Yes. Any other questions? Yep.
Gravitational waves or stochastic backgrounds, the only thing that can cause the B-mode polarization, or like how do you go about distinguishing, other types of things that can cause difference?
Yes, so, okay, so here I can go into two, there's the CMB, when we look at it, there's 4 grounds, so you might ask the question, is the polarization of something else, the synchrotron from our galaxy, does it have both E and B modes or gradient and curl? I can answer that offline if you want. Let's go back to just some primordial thing, okay? So it turns out that when you decompose the most general fluctuations that you can think about can be decomposed into 3 types called scalar, vectors, and tensors, okay, of the metric fluctuations. So it will turn out that through the similar, parity and symmetry arguments, density fluctuations, which is the scalar mode, is the one that can only create those. Vector and tensors can create all of them, okay? So in principle, if the universe is filled with something that creates a lot of tensor vector modes, you will also create this pattern. In fact, during long time in the field, but long time ago as well, people were having an alternative model for the origin of fluctuations, which was not the abracadabra from before the hot Big Bang, but something happening there, like a network of cosmic strings or something like that. Those generate density, vector modes, and tensor modes. And when you look, they create both the E modes and B modes. And the B modes, their origin is both the gravitational wave that they create and the tensor modes that they create. So, but in this context in which the fluctuations are produced from before the hot Big Bang and they were outside the horizon for a long time, the only thing that survives to this side are the density fluctuations and the tensor modes for reasons that I can go offline for you. So there would be no vector. So But in principle, you should look at other properties of how the pattern on the sky changes when I change the wave number, the angular scale, that will tell you which one it is. But at the level of these, also the B modes can be produced by vector modes. Any other question? Okay, it's not raining, or at least not as badly that I can see it from here. So maybe it's a good time, and I'm also super. So let's finish here.